Yesterday we introduced the idea of a limit, and the idea with a limit was that it was a tool that we can use when our other tools, typical ways of approaching what's going on with a function, don't work, or give us some sort of indeterminate or undefined answer. So just to quickly show, yesterday we started with the idea of a parabola, just a continuous polynomial function. And as I change the value of a, right, my point moves around. So if I make a, -3 or let's say -2, right, then the y value is simply 4, right? And we know this. You plug in -2 to the equation, you get 4. Now, when you are looking at a limit on a continuous function, on an ordinary function, the limit is really no different than just subbing in the value, right? Like, if I take the limit as x approaches -1.95 of x squared, I get 3.8. I mean, I get, probably more than that, 3.8025, right? But if I just subbed in -1.95, I would get that answer, right? And so this demonstration here is just meant to illustrate that when you're looking at a continuous function, and, remember, every polynomial is continuous, for instance, your limit is no different than just, what's the point doing at that specific place, right? That's really all there is to it, right? So the limit is simply, evaluate the function at in that area, and you'll be fine. Now, suppose we made this function a little bit more complicated, like something like x over absolute value x. Now, here, right, I can sub in a in many places, and my limit is +1, and my function is +1, right? And the limit is the same as simply subbing in the point anywhere you want, right? Except when you get to right at this particular spot here. Now, at this particular spot, right, at a equals 0, we don't have a limit, and we don't have a value either, right? It's undefined at this particular value because my function, 0 is not in the domain. Now, if we put 0 in the domain, let's just quickly change this. So I'll say if x is equal to 0, we'll make it 1. Otherwise, we'll make it that. Maybe like this. Okay, so what did this do? This gave me, now I have a function that's actually defined at 0, right? So let's just go back for a sec. So same point, the limit and the function are the same. They're always equal to 1. And then as soon as I get it down to be at this exact point, right, my function exists. F of a is equal to 1 because it's a filled in dot, but the limit doesn't. Okay? It is possible for the function to exist, but the limit not to exist. And that's what you see in this situation. And the reason is because if you look at the limit from the left side, the limit on the left side is moving you towards -1. The limit on the right side is moving you towards +1. Since those two limits do not meet, right, we say that this limit doesn't exist, and even the computer program doesn't know what to do with it, right? It can't give you a limit here because it looks at both sides and they don't agree. So we said if the right-hand limit and the left-hand limit do not line up, you don't have a function, a limit at that point. Let's try one other alternative. So let's do x minus 2 over x squared minus 4. Okay, so here's a function, and you can see if I check the limit, at any of these places, I can check the limit at all these places, and everywhere I check, it's the same as the function. Now, if you were looking carefully, you might have noticed there does seem to be a point at 2, right, where the function does not exist. You see how it can draw a point at 2.5, it can draw a point at 1.5, but as soon as I get it to try to draw a point at 2, it can't. Because of course at 2 there's a hole, right? And if you don't remember why, then just factor this equation and cancel, and you'll see that the x minus 2 cancels from the top and the bottom, right? I wouldn't worry about that so much, because we're going to talk about how that works a little bit more later today. That's just a review from advanced functions. But in this situation, okay, when a is 2, so the limit as x approaches 2 of this equation, the limit clearly exists. The limit is 1/4, right? You can see this side is coming towards the value of 1/4. Let's just zoom in a little bit, right? So 1/4 would be, right there. The left side's coming at it, the right side's coming at it. They both, converge on this particular point, but that particular point isn't there. Okay? And this is a situation, this is sort of the third situation where there's a hole in the function. If the hole exists on an otherwise smooth line, we say the limit exists, even though the function doesn't. So there's sort of three cases here, right? The function can exist, and the limit can be defined, like it would be in any parabola or straight line or cubic or any polynomial. The function might exist, but the limit doesn't exist. That would be in the case of the one we were just looking at with the jump, where it jumped from +1 all the way to -1 with nothing in between. The third situation is this one, where the function itself does not exist. There's a gap, there's a hole there, but the limit still does. So here, the limit exists. The limit is 1/4. And you can get as close as you want to 1/4 in this function by plugging in numbers close to 2. For example, if I plug in f of 1.999, I get a number very, very close to 1/4. Remember, 1/4 is 0.25, so 0.2501. I'm within 4 decimals of being equal to 1/4. I can make this even closer, right? Where I need whatever 10 decimals to tell the difference between my number and 1/4. I can never get it to equal 1/4, but I can get it to equal as close to 1/4 as you could ever need, as you could imagine, right? So that's what a limit is, right? That there is no point here, but there's still a value that the function approaches. That's a limit. Now, something else we should point out while we're on this graph, if I go towards an asymptote, okay, so let's move towards the asymptote. So look, the limit is 5, the value is 5. Okay, the 6.6, 6.6, 10, 10, 20, 20. Now here, the computer tries to evaluate what's happening at -2, and it tells you that the answer is -infinity. I mean, this isn't really an answer, right? Because infinity is not really a number, at least not the way most numbers we're used to. So we're not going to say that there's such a thing as a limit that's equal to infinity. I mean, just think about the definition of the word limit, the everyday definition of the word limit, and the meaning of the word infinity. I mean, infinity means without limit, right? So you can't say that the limit is positive or negative infinity. We just say the limit does not exist. And we didn't cover that yesterday, but this is a piece of new information. If you have an asymptote, right, as we do here, you cannot plug in the value -2 into this equation. And furthermore, if you try to pick numbers close to -2, okay, let's try a couple. -1.99, -1.999, excuse me, it would help if I typed F there. Right, that the more of these things I type in, right, F of -1.99999, you can see I'm not approaching a limit, I'm actually escaping a limit, right? I'm like growing without boundary. The closer you make your number to -2, the closer the function, or the farther away your function gets. So this is not a limit, this is the opposite of a limit, right? This is an infinity, right? Where the function just keeps growing without boundary or without limit. So if you come across a vertical asymptote and you're asked, what is the limit as x approaches -2, you say it's undefined because there's an asymptote here. And if you need to prove it, plug in a number like negative 1.9, then plug in 1.99, and show that it's not getting closer to a number, it's getting farther away from 1. It's growing without bound. Okay. Now, so let's just summarize some of that in terms of where we got yesterday. First of all, if you are ever doing a limit question on an interval of a function that is continuous, okay, and remember, continuous means there are no breaks, gaps, or holes. A kind of everyday common sense definition would be a part of the graph you can draw without raising your pencil. Now again, this part of the graph I can draw without raising my pencil until I get to 2, because there's a hole at 2, right? My pencil would have to come off the page, and then it would have to continue after the hole. So every swipe of the pencil is a continuous section, but there can be breaks in the continuity of your function at different places. If you know there are no breaks, gaps, or holes, and you're not worried about that in the interval that you're talking about, the limit is always just equal to the point. And that makes this very easy, 99% of the time, because all you're doing is subbing in the value. Now, of course, by the same token, we're not really interested in that 99% of the time because we already know how to do that. We're interested in how do you tackle, problem areas, places where I don't know what the function is doing, or it's undefined, or some other, problem that I'm having that I need to get to the bottom of. That's where a limit is useful. So it is true that you can use direct substitution. You can just plug in a number to get the limit much of the time. But don't expect a lot of questions like that, because that's not the skill that we're really trying to figure out here, right? I mean, I just want to make sure we don't sort of oversell this, right, in terms of like when you use limits. Let's look at an example here. I think this illustrates it nicely, right? So this one, it's a polynomial function, and it's a straight line there that they've got. You can tell me the limit anywhere you want on that line by simply finding the point, and you're done. Like this is very, very, very straightforward. So for instance, if I oh, sorry, I gotta fix my tablet again. I'm on my other page. Okay, I want to go on monitor 1 today. That should hopefully do it. Okay, the limit as x approaches 0 of x plus 1. Okay, look, I just plug in 0 plus 1, I get 1, and that's it. Right? What's the limit as x approaches 0? It's 1. It's just the point that's sitting there. There's nothing fancy happening here. There's nothing special. And the limit is as straightforward as plugging in the number and writing it down. And don't let them fool you by approaching it from the right or approaching it from the left. Look, if the limit exists everywhere on the function, then the left and right limits exist and must be equal to each other. So all of this, when you're looking at a polynomial, you can just assume. Right? The limit of any polynomial, just plug it in. You may get one of these questions, but as I say, don't expect a lot of these. This is just to kind of get us warmed up. Again, here, it looks complicated, but it isn't. It's a polynomial, therefore it's equal to f of a, whatever the limit is asking you to look at. In this case, it's asking you to look at 2. So we get 2 squared plus 2 times 2 plus 1 is 9, and that's all there is to it. Here again, what is the limit as x approaches -1 from the right? Again, I know that the left-hand limit is equal to the right-hand limit for all values of a on a polynomial. And x cubed is a polynomial because it doesn't have any, there's no x in the denominator, there's no roots, there's no exponents that have variables or whatever. Right? So because the right-hand limit is equal to the left-hand limit everywhere on a polynomial, I don't care that it says from the right. That's irrelevant to me. Right? I'm just going to sub in -1. I go -1 cubed, and I get the answer -1, and that's that. Again, if you ever needed to check a limit and you weren't sure, it's a fairly simple way of doing this. Change your function to, so type in GeoGebra the function that you want to analyze, right? So I typed in f of x equals x cubed, and then I'm going to type limit. And when I type limit, let me just pull this up a bit. When I type limit, it tells you what it wants, right? It tells you what function are you talking about and what value do you want to check. By the way, it also has a function for right-hand limit and left-hand limit. Above would be right-hand and below would be left-hand. But anyway, I don't think we need to go into that just now. So let's go limit. The function I want to know is x cubed. and the value I'm interested in is -1. And of course it comes back with the number -1 because this is not a complex function, and all you have to do to get the limit is simply sub in the value, and that's where I'm getting -1 from. So again, if you get a polynomial limit question, you just say thank you for this gift and you go on to the next one, right? Plug it in and that's it. Now, where of course this is more useful is when you start to get into trickier functions with problematic, values, undefined values. So a rational function, as we've been learning since grade 11, and when we certainly covered a lot in grade 12, they have a function in the denominator, and that function in the denominator causes issues when the denominator is equal to 0. Now, looking at this first one, it says limit as x approaches 3 of 1 over x. So I'm just going to type that in literally. Limit 1 over x approaches 3. What does it do? It comes up with 0.333. Now, why would it do that? Because this is equal to f of 3, which is equal to 1/3. Right? All I did is plug in the 3. If you can plug it in, right? You try to do that here, though. F of -2 equals 2 over -2 plus 2, and lo and behold, you get 2 over 0. That's a problem, right? So here we get this issue that direct substitution doesn't work. Okay, you can't do direct substitution there because it gives you undefined. And as we have already learned, just because the function is undefined doesn't necessarily mean the limit is. It might be, right? It could be one, it could be the other. We don't know yet. It's possible there's a limit, it's possible there's not. Now, if you look carefully at this function, if you remember, what this function is going to do, it's going to have an asymptote here at -2, and it's also going to have a horizontal asymptote at 0, right? Now, we know that when x is a positive number, like positive 10, you'd have 2 over 12, which is also a positive value, so your graph's going to look something like this. Again, I don't know exactly, but I don't really care. On this side, it's going to look something like that. Now look at that graph. As x approaches -2, does the limit exist here? If I approach it from the left, I get larger and larger and larger negative numbers. Left-hand limit does not exist. Right-hand limit does not exist. Well, guess what? If either the right hand or the left hand don't exist, right? You can't say the limit exists. All you have to do here is say asymptote dne, right? So limit x approaches -2 of f of x does not exist. If you need to give a reason, you say it's an asymptote. And if you're really stuck, if it's like if it's a complicated one and you just want to prove that it's an asymptote, the easiest way to prove an asymptote is make a little table, plug in -1.9, plug in -1.99, plug in -1.999, and show that these numbers do not converge, rather they diverge. Again, let's just quickly do that so we have the example. So f of x here was 2 over x plus 2, and I wanted to check. So here at -1.9, okay, the function's equal to 20. At -1.99, the function's equal to 200. And at -1.999, the function's equal to 2000. So what's happening here? It is diverge. It diverges. It doesn't converge on a value. It diverges off to infinity. So I just say it diverges, therefore there is no limit. So again, if this is a knowledge question, then you say the limit does not exist because it's an asymptote. If this is a communication question, then you go and show me the logic behind your decision. You tried to sub it in, didn't work. You analyzed the graph, you saw that it was an asymptote, you concluded the limit does not exist when there's an asymptote. Say you didn't know how to graph, it was more difficult than this, and you couldn't just do a quick sketch. If you want to check what's happening at a point, test values closer and closer to the point. You're either going to notice that these numbers on the right converge on a value, in which case you do have a limit, or you're going to notice these values diverge and get bigger and bigger, and therefore you do not have a limit. Okay, and that's what you're doing. That's what you're doing here. I'm fairly confident when I say if you ever get a situation where you have number over 0, that is always going to be an asymptote. If you have 0 over 0, you have to be careful. It could be an asymptote, it could be a hole. So the limit might exist or the limit might not exist. If you see number over 0, like we did, 2 over 0, that's an asymptote. So there, you can conclude at that point, there's no way this is going to be a hole if you have number over 0. If you have 0 over 0, that one you have to investigate, right? You either have to do this check or graph it, or as you'll learn in a minute, we have some other tools for dealing with this. Okay, a root. Now a root function is one place where my normal rule about left-hand limits and right-hand limits is a little bit different. So let's analyze the root here, and we'll just take it in the same sort of approach we've been using. So we'll change this to square root function, and let's take a look at the square root. Now, of course, the square root is a continuous function on its domain, right? So I can look anywhere I want to look, and sorry, I see what I've done here. These are kind of in the way. Okay, there we go. Is that sort of working? No, it isn't. There we go. Okay. As you can see, on the domain of a root, anywhere you want to look, the limit is simply equal to the value of the function, and then that's as you should expect, because everywhere along this root it's continuous, and the two sides point to the same value. There's no gaps, there's no asymptotes, nothing like that. So limit's fine on a radical. Now, what about the starting point? Because of course, you should be thinking to yourself, well, what about right at 0? Like, what's going on at 0? Now, at 0, the limit exists and the value exists. And you might say to yourself, well, wait a minute, how can the limit exist? Because there's no left-hand limit. There's a right-hand limit. I can come at it from the right, but how am I going to come at it from the left? There's no values to speak of. This is kind of like an exception to our rule about the right-hand and left-hand limits. The limit does exist at 0 because when you are on the border of a function's domain, you only have to look from the side that actually exists. Okay, which is a bit of a technical point, but just make a note of it. Right, so I'm just going to add a c here in the middle. The limit as x approaches 0 of root x equals 0. That's true by that's a definition. It's part of, and we're going to say even though there's no left-hand limit. And the reason there's no left-hand limit is because it's outside the domain. So again, you can say that this function's limit is still there, even though it only has a right side limit, because there is no function on the left side of it. Okay, that is different from looking at the one we looked at the beginning of the day, right, where it did this. This has a right-hand limit, and it has a left-hand limit, and they are different. But suppose this didn't exist, then it would be fine, right? This point would be fine, because it would, you would come at it from the right. It would be this value. It doesn't exist from the left, so you leave it as that value. Okay, and that's just kind of one little exception to our rule about you need a left-hand limit and a right-hand limit. I don't think that comes up very often, but just so you know, that would be the answer. Again, here, there's nothing to this. You simply take your value, square root 4, you get 2, you move on. You plug in 2, you get square root 9 is 3, it's done. So very, very, very simple, right? Root functions are not going to give you a problem. At least the basic root function is not going to give you a problem, because everywhere you want to look, you simply plug in the number and you will get the value. Again, you cannot plug in negative numbers, obviously, because there's no function, but it is okay to plug in 0 and say that the limit exists there, even though it only has one side. Okay, trigonometric functions. Trigonometric functions are also very, very straightforward. There's no sorry, I should say it says trigonometric. Really, it should say. Let's clean this up a bit. Really, what I mean here is sinusoidal. Because of course, if you think about tan x, this is untrue. Right? Let's just do a very quick demonstration of this. Okay, so let's say f of x is sine x. Now again, you can look anywhere you want on this graph. It's continuous everywhere, and its limit exists everywhere, and its limit is simply equal to, whatever value you plugged in, no problem. So, there's nothing to getting a limit on a trig graph. You just plug in the value. Now, again, to be clear, when I say trig, I should be saying sinusoidal, because obviously if I make the graph tan, right, there's an asymptote, right, an infinite number of asymptotes, and you don't have a limit where you have an asymptote, right? So, here at pi over 2, so if I let a equal pi over 2 for a sec, well, except that every time you hit spacebar it animates. Okay, if I make a pi over 2, you notice the computer still tries to calculate a number just because it's, it has to round at some point, right? But it knows that the limit isn't there. There is no limit, right? Because you're talking about an asymptote. So just to kind of clean this up a little bit, I would change this to say sinusoidal, which is continuous for all values of x, and direct substitution can be used, for any time you need to do one of these. So you plug in pi into sine, right? So let's graph it again. F of x, we'll just change it with sine x. And if we plug in pi, which is right here, 3.14. Sorry, GeoGebra animating itself is the bane of my existence. We'll surely run into that problem many more times before the year is over. Okay, right here around pi, you can see the value is 0. If I plugged in pi itself, of course I would get 0, but it's close enough. What if I plugged in 0? Cos of 0 plus 1. I'm not really okay, so cos of 0 is 1, right? If you plug in 0 into cos x, you get 1, so you get lim. As x approaches 0 of 1 plus 1. Sorry. 1 plus 1, and you just get 2. Again, if you want to see it, cos x plus 1. And what is this function doing when a is 0? It's equal to 2, right? Straightforward. Just plugging it in. Okay, again, this is a really good example to do just, again, it's a polynomial, so sub in. And of course, if you sub this in, you're going to get the answer 2. This is a polynomial. Sub in. You sub in 2, you're going to get the answer 5. Here, as x approaches 1, okay, now let's do this like it was on a test. What would you do here? What's the correct way to answer this question on a test? And again, if we're talking about knowledge, right, then, for knowledge, I'm just looking for right or wrong type of thing. If we're looking, if it's communication, I'm not just looking for right or wrong. I'm looking for how do you express your point, right? Have you made a mathematical argument? Is it true? Is it logical? Let's give a good answer for this. Okay, so limit x approaches 1 of f of x. Okay, we're going to start by determining what happens as x approaches 1 from the right side. Okay, and if I look, it approaches the value 4. Then I'm going to look, what about as x approaches 1 from the left side? And I notice it's negative 4. So the limit, remember how you write this, the limit as x approaches 1 from the left of f of x is equal to negative 4. Then I'm going to say the left-hand limit is not equal to the right-hand limit, and therefore limit as x approaches 1 of f of x does not exist. Okay? There's nothing, if you write it out like this, there's nothing I can say, right? Try and think of it from that point of view. Could there be a fault in what I've written? Have I left something out? Have I assumed something? Is something not clear? Right? That's where your goal is in communication. Clarity, completeness, right? And cogency, just for 3 C's. But cogency is about logic, right? Make sure it's logical. Make sure there's no possibility to misinterpret what you've done, and that you've clearly gone from beginning to end answering the question. Okay, so here's what I've said. Someone is going to write, the limit does not exist because the two sides don't match up, and that person is going to get 60, right? Not because they don't have the knowledge, because they don't have the communication. Okay, so like I said, if this is a knowledge question, and I ask you, does the limit exist as x approaches 1? You say no, because looking at it from the right, looking at it from the left, they don't match the same value. No problem. If this is communication, you give me a mathematical argument, right? You state it clearly using your mathematical language. All right? Okay, so again, when it says explain why, that's what I've done here. By the way, you can explain using words as well. I'm happy to see answers written in words, and many answers in the course you are going to have to use words. But again, whether you need them or not, is up to you in a situation like this. You could explain this using words and be fine as well, right? That would be no problem. Okay, so there's a bit of homework there. Again, I'm going to ask if you have questions with the homework. What you do is you go to the discussion forum, go to calculus. I'm going to make a forum for Unit 1. And then you post the page, the number, and the question. Type out the question, please, rather than make the people who want to help you go look it up. A question like, how do I do number 6? I'm probably not going to answer that. Okay? I'm going to answer a question like that's asked like this. Hey, for number 6, which says, and give me the question, I tried blank, or I thought I had to do blank, or, I got stuck after I did blank. Show me that you have taken a step. Show me that you have tried something, right? And then, I will help you take the next step. I don't know how to do number 12. I can't help you with that, right? Because what I'm going to say to you if you say that is go back and watch the lesson again. Go back to the point in the lesson and at least get the first step, right? And tell me what you did. Tell me what you did. Now again, if what you did is I wrote down the question, I defined my variables, and I just couldn't set up the first, I couldn't set it up or something like that, that's fine, right? I need help setting this one up. I know the variable is this, or I know, tell me at least what you do know. Show me that you've engaged with the problem, and you're not just asking me to do your homework for you. Okay? That's what I'm going to ask of you. Let's continue and finish up here with properties of limits, part 2. So again, this part where we're doing, now we're going to kind of get into the meat of like why you learn limits. Of course, it's nice to do these ones where we're just doing direct substitution. But today is about like what are limits for and how do we use them to solve problems that have come up in previous courses. Okay, so again, evaluate the limits. If the limit does not exist, explain why. I just did this one, right? This is the same picture as the one on the other page. So I'm just going to say C, previous. Okay, what about as x approaches 3? And I think that's a plus sign. Sorry. I see zooming it in has not enhanced it, contrary to what CSI would have you believe. It looks like 3 positive. So as x approaches 3 from the right, f of x approaches -2. It's okay to say that, right? Because we're only looking at the right-hand limit only. We're not looking at both. So if I asked you what's the limit as x approaches 3, you'd say it does not exist. But if I ask you what is it approaching 3 from the right, no problem. It's -2. What about as x approaches -1? Again, no problem. It looks like about -2.5. I don't know, right? But something like that. 2.6 maybe. It's a little bit below half. What about as x approaches 0 of this equation? 1. I just plug in 0. It's a polynomial. I'm not going to get tripped up by a polynomial. Polynomial, I just plug in the number. An exponential, we didn't talk about exponentials yet, but if you think back to what an exponential looks like, the limit as x approaches a of f of x equals f of a everywhere for an exponential, because an exponential is continuous everywhere. So I'm just going to plug in -1, I get 1/4. Done. What about the limit of 2 as x approaches 3? Well, look, this is the graph of y equals 2. As x gets close to 3, y is still 2. In fact, nothing x does on this graph is ever going to change the fact that the y value is 2. This graph, again, I know this is an asymptote, because if I try to do f of 1, I get 3/0. I know that's a condition for an asymptote, and then I say the limit does not exist. Again, if this is a communication question, I'm not going to write this. I'm going to write this. I'm going to write the proper proof. Okay? Don't mix this up between, what I'm trying to show you in terms of making sure we understand it and writing out a proper formal answer. I don't want to take a proper formal answer for every single thing we do, right? I don't think it's necessary. It's going to slow us down too much. But, know the difference between what you're being evaluated on. If you're being evaluated on knowledge, this is fine. If you're being evaluated on communication, maybe you think to yourself, I should probably give more here, right? I'm not showing that I really get this, that I can really express myself the same way. Okay, now the big key about limits, right? So basically, what do we know? If you're looking at a continuous function, you plug in a value and you get an answer, you have your limit. Easy. If you're doing a question and you plug in a value and you get a number over 0, you have an asymptote. No limit. What do you do when you get 0 over 0? Now remember, number is defined. Number over 0 is undefined. 0 over 0 is indeterminate, which means we don't know what it is. Indeterminate, right? It's not determined. We don't know if it's a limit, if the limit exists, or if it's an asymptote, right? So this is why we have to investigate 0 over 0, because sometimes it'll produce an asymptote, sometimes it'll produce a whole. Depends, right? Let's take a look at an example. Evaluate the limit as x approaches 4 of this equation. Of course, if you plug in 4, you're going to get 4 squared minus 16 over 4 minus 4, which is going to give you 0 over 0. As soon as you see 0 over 0, you think to yourself, okay, it's indeterminate, so I've got to try and use a strategy to see if there's a way to fix this up. The first strategy I'm going to show you is factor, cancel, then try to substitute. You couldn't substitute at the beginning. If you tried to substitute at the beginning, you ended up with 0 over 0. You don't know what 0 over 0 means, so you haven't really helped answer the question. Is there a limit or is there not? This doesn't help me, right? We don't know. So what can we do? We try to factor the equation. We try to cancel anything we can cancel, and then we're going to try to substitute again. Observe. Limit as x approaches 4. Okay, I'm going to factor the top. Now the top is a difference of squares. So x minus 4 and x plus 4. I notice that I've got something here where everything is in a bracket. There's no addition or subtraction that's outside a bracket, so I can go ahead and cancel, and I do so. And now I see that this limit is just x plus 4. And that's easy to do. I just plug it in. And now I can plug it in. Okay? So what does this tell me? The limit as x approaches 4 of x squared minus 16 over x minus 4 is equal to 8. Let's prove it. Okay. Let's change this. So we're going to change this function to x squared, sorry, you got to use brackets here. So x squared minus 16 over x minus 4. All right. So this is the function we're looking at, right? X squared minus 16 over x minus 4. And I'm just going to change this for a second. So we're going to do a plus 0.1, and then a plus 0.01, and then a plus 0.001. Good. Okay, now let's get rid of some of this stuff just so we don't have the confusion. Okay, so it's asking us to investigate what's going on in this function when x is 4. So let's put x as 4. Now we claimed that the answer should be 8. And you can see that the function does not exist when x is 4. Because there's a hole, right? The function does not exist, but the limit does exist. And so if you had to draw this, right? You draw this graph and you draw an open circle. You draw an open circle right here, and you'd say open circle hole at 4, 8, right? So that's where the hole is located. And sorry, I don't know why I've drawn it at 8, 12. It should be down here, sorry. Lost track of where we were. Okay, so there's a hole at 4, 8. The function isn't there, but the limit is there, right? And if you look at numbers, if we check, 4.01 or 4.1, 4.01, and 4.001, notice that our values get closer and closer to 8 itself. They're not going away from it like an asymptote. They're getting closer to it, and that's why you have, you have a limit here. So remember, you can always check a limit if you want. You can sort of brute force check it. But making a little table, check 4.01, 4.001, 4.0001, right? And notice that, you get 8.01, 8.001, and so on. The closer you get to 4, the closer your value gets to 8, and therefore your limit exists. But the whole point of doing it this way I was showing you earlier is try to avoid this, right? So we don't have to crunch so many numbers all the time. Try to sub in as a first step. So I'm going to write a step 0. Substitute. Of course, most questions, what will happen is you will try to substitute and you won't be able to, because if it works, then there's not really a lot to do, right? If substitution works right off the bat, then you're done. So expect most questions when you substitute right off the bat not to work. Then you're going to try to factor them, you're going to try to cancel them, and then you're going to try to substitute again. Sometimes that will work. Sometimes that will find the problem, right? And you'll be able to get to a value. If this doesn't work, then we're going to say 4 would be check nearby values, i.e., 4.01, 4.001, 3.99, that sort of thing, right? You can check nearby values. I would say that step 4 is always a last resort, right? So no matter what question you're looking at, you can always do that step 4 to at least show me you understand the idea. You may not get the perfect right answer doing it that way, but at least you'll get a level 3, right? So as opposed to getting a 0 or a 1 out of 4, let's say you get 3 out of 4, for at least showing me that you understand what I'm asking and you have a technique to get close, even if you can't get the exact answer. Okay? Let's try a couple more. Again, notice right off the bat, if I sub in 2, I get 8 minus 8 over 2 minus 2, which is 0 over 0. So of course, it's like I say, don't expect that to really work much. Maybe one question, right? So let's try the other way. So what can we do here? We can factor the top, right? Take out a 2. Now again, if this is a communication question, I'm going to have to write limit x approaches 2 all the way down. It's a pain, but if you're being evaluated for your ability to communicate in the correct format, then that's what you have to do, right? Again, if this is an application question, knowledge question, thinking question, and you forget to write limit x approaches 2 on a line, it doesn't bother me. I'll know what you mean. But if it's communication, I am marking your ability to follow the conventions. So follow the conventions. Okay, here we go. I'm going to factor the top. X minus 2, x plus 2. On the bottom, x minus 2. Okay, I'm going to because everything on the top is multiplying and everything on the bottom is multiplying. If there's any addition or subtraction, it's inside a bracket, so I'm good to cancel. So this means what I'm really asking is the limit as x approaches 2 of 2 times x plus 2. I know how to do this. I'm just going to plug it in. And this is equal to 8. Right? So I plug in 2 and I get the value 8. Again, it doesn't hurt to take a second to draw it and double check. But let's just change our function here. So f of x is equal to 2x squared minus 8 divided by x minus 2. That's what the function looks like. And then if I make my a value here equal to 2, Notice the function does not exist, but the limit does exist, and the limit is 8. So I'm done. Again, you can imagine this can get more and more complicated just by making the questions themselves a little bit harder. But here we have a difference of cubes on the top, and then we have a sum product on the bottom. Remember, when you're factoring a difference of cubes, you have a cubed minus b cubed. We copy the sign in the first bracket, and then remove the sign in the second bracket, right? And I'm just going to make sure I actually did that right. Okay, so cube root the x cubed, you get x. Cube root the 8, you get 2. The little bracket is x minus 2. You copy the same sign as the question. In the other bracket, you do the first term squared, the two terms combined with the opposite sign, and then the last term squared. So again, maybe just take this down as a quick, if you don't remember this one. Okay, so notice if it's a difference of cubes or a sum of cubes, right? Sorry, this does not look good. I'll try to zoom in and clean this up a bit. Okay, if it's a difference of cubes or a sum of cubes, the pattern is very, very, very similar. The only thing that changes is in a difference of cubes you have negative here, positive there. In a sum of cubes you have positive there, negative there. Everything else is the same, right? So you should know that one, but at least for now have it written down somewhere you can quickly access. All right, so limit as x approaches 2. If I factor the top, I get x minus 2, x squared plus 2x plus 4. Remember, in my difference of cubes pattern here, a would be x and b would be 2, right? Because the cube root of 8 gives me b, and the cube root of x cubed gives me a. On the bottom, I need two values that add up to negative 3 and multiply to positive 2. Those numbers are x minus 2 and x minus 1. Okay, so that's how you factor the bottom. Now, the difference of cubes always looks like this can be factored. It never it's never factorable. So don't waste your time on it. If you did a difference of cubes, I shouldn't say that, sorry. It might have a GCF. It might have a GCF. Okay? But you're never going to be able to do a sum product or a decomposition or something. And I'm just going to say, except for GCF. You might have a GCF, but you probably took out a GCF earlier, honestly. Anyway, you can't factor that. You can't do anything with it. Don't waste your time on it. What you can do here is notice that the top is 2 brackets, the bottom is 2 brackets, all the addition and subtraction is inside a bracket, so we're good to go ahead and cancel. And then we can say the limit as x approaches 2 of x squared plus 2x plus 4 all over x minus 1, and that is simply equal to, now we can just plug in a number, right? 2 take away 1 on the bottom is 1, 2 squared plus 2 times 2 plus 4 is 12 on the top. And our limit's 12, right? So what is that function doing as x gets closer to 2? That function is getting closer to 12. Let's demonstrate that. Yeah, my difference of cubes here we don't need. Okay, so the function we were working on was x cubed take away 8 over x squared, squared take away 3x plus 2. Right, that was the function we were looking at. Now notice, if this function asked you about 1, you would have to say there's no limit. As x approaches 1, you would not get a limit here, right? But this question was asking us about x approaching 2. When x approaches 2, right, we see that the function does not exist because there's a hole, but the limit does exist, and the limit is 12. And again, how do you get the limit? You just do what we just did, right? Factor it, cancel it, sub it in. Okay? So that's doing limits with factoring. Now there's one other tool we're going to learn here. Yeah, simplifying rationals too. Okay, what are we at here? 50 minutes. Okay, I'll try and pick up a little bit of speed. One other tool we're going to learn here is called rationalizing the numerator or denominator. So here's a problem, right? When you get to this question, if you try to, so our step 0, right, is always plug in the value and just see if you got an easy one. We do 9 minus 9 over root 9 minus 3, which is 0 over 0, and not entirely unexpectedly, this is not an easy one where we need to do more work. So the question is, what do I do, right? What do I do when I have a root like this? This is a technique called rationalizing. You know what? Rather than say that, let's just say what I'm going to say is use the conjugate. Okay, use the conjugate. Now, what is the conjugate? How do you get rid of a root? How do you get rid of this root here? Let's think about the bottom for a sec before we go any further. X minus 3. How do we get rid of a root? Now, normally, what you think to get rid of a root is you square something. So what if we squared this? Right? We'd get root x minus 3 times root x minus 3, and that gives us root x times root x, which is x, root x times negative 3, which is negative 3 root x, negative 3 times this again is this, and then we have minus 9. So I tried to get rid of the root, but I actually just made it worse, right? This is worse than what I started with. It's 3 terms instead of 2, and I still have a root where I wanted to get rid of it, right? So when you square a binomial, i.e. 2 terms that have a root in them, squaring it is not going to get rid of the root. That's not what we want to do. Instead, what we're going to do is use the conjugate. Now the conjugate is kind of like doing a difference of squares in reverse. What does the conjugate say? It says take the same thing but change the sign in the middle. Okay? This here is the conjugate. So root x minus 3, I'm going to multiply it by root x plus 3. What happens when I do that? Root x times root x becomes x. Root x times positive 3 is plus 3 root x. Negative 3 times this is negative 3 root x. And then negative 3 times 3 is negative 9. And now I get x minus 9, and I have no root. And that is key, right? So when you want to remove a root from an expression, right, don't square the expression unless you want to square the whole thing, which, as I'm telling you right now, if you square a binomial, you're not going to get rid of the root signs. Okay? If you want to get rid of a root sign where you have a binomial, use the conjugate. Okay? So write out, the exact same thing, but change the sign in the middle. So let's see how this would work here. Remember, if I'm going to multiply the bottom by something, I also must multiply the top by that thing. So I'm going to multiply the top and the bottom by the conjugate. Now, of course, this is going to move the root to the top, but as you'll see, that actually solves our problem for us. Again, not going to lose marks because I forgot to write the limit. Just going to be in the habit of doing that all the time. Now, what happens here on the bottom? As I showed you on the right side, the bottom becomes x minus 9, right? That's what happened when we multiplied it by the conjugate. We did FOIL, right? Root x times root x was x. This was negative 3 root x, positive root 3x, and then negative 9. Now, how is that useful in our question is, look what happens when you multiply the top and bottom by the conjugate. Oh, look, all of a sudden, I've got a bracket that's repeated on the top and the bottom, and I end up with limit as x approaches 9 of root x plus 3, and I can sub into that. Right? I can sub into that because I've canceled out the problem. The problem was that I had an x minus 9 on the bottom, right? And I don't have that anymore. So I can go ahead and just plug in 9 at this point. Square root of 9 is 3, plus another 3 gives me 6. Again, let's check this one, and then I'm not going to check any of the other ones, just so I have some hope of finishing this in 75 minutes. Fx is equal to x minus 9 divided by square root sqrt x minus 3. Okay, so this is the equation we were asked to analyze. If you plug in 9, which I'm going to need to change my rules here, so I'm going to allow you to get up to 10 here. So if we plug in 9, okay, the limit exists, and the limit is 6. The function does not exist. Right? Perfectly consistent with what we said. It didn't work when we tried to sub in at the beginning, so the function isn't there, but the limit is still there, and the limit is 6. Okay, let's take out a couple other ones just while we're going. How do you deal with this? What's the conjugate here? That's the real question. So limit x approaches 0, root x plus 1 minus 1 over x. The conjugate here is the same thing, exact same thing, but a different operator in between the two terms. Don't change this, because we're not changing the terms themselves. We're changing the operator in between the terms. And of course, if we do that to the top, we have to do it to the bottom as well. What is this going to do when we FOIL this out? So limit as x approaches 0. By the way, I'm not even going to, of course you could sub in 0 here at the beginning, but if you do, you'll see that it's 0 over 0, and subbing in doesn't do anything. Okay, let's FOIL the top. Root x plus 1 times another root x plus 1 simply removes the root sign, right? Root x plus 1 times positive 1 is plus root x plus 1. So I'm going to zoom in a little bit to make this a bit neater, hopefully. I'd like to say by the end of the last time I was teaching virtual math, I was pretty good on this tablet, but the truth is, I'm not. Okay, next, so FOIL. We did first times first, outside times outside, inside times inside we're doing next. It's a negative 1 times this root, okay? And then we do last times last is simply minus 1. We don't really need a bracket up here. It's fine. On the bottom, I'm not really interested in distributing this because, why would I want to distribute it? I'm just going to leave it factored and see if there's anything I can cancel. Now what happens on the top? A positive root x plus 1 and a negative root x plus 1 cancel to become 0. A positive 1 and a negative 1 cancel to become 0. And what you're left with here, once you've sort of added all those like terms or opposite terms, is this. Again, this on the bottom is multiplied, so feel free to cancel it. And what we get here is the limit as x approaches 0 of 1 over root x plus 1 plus 1. Okay, so plug in 0 into this and you get 1 over 2. If you put in 0 here, 0 plus 1 is 1, square root of 1 is also 1, and 1 plus 1 is 2. So you end up with a final answer of 1/2. Okay, and that would be the limit in this case. Once again, all we've done is use the conjugate to get that answer. For this one, I'm going to post this one to discussion. I think you have the tools you need. Do I have the tools I need? What is happening here? Okay, seem to have run into a bit of trouble with my tablet. Did I hit something I wasn't supposed to? Okay, there we go. Alright, sorry about that. It's bound to happen sooner or later. I'm going to post this to discussion. So go ahead and do it. It would be good to practice. You can either do it on a piece of paper and upload the picture, or use the equation editor on the thing. The equation editor is it's when you open up a new discussion post, look for that. It's the equation editor. and see if you can answer it, right? Try it. See if you can figure out what the conjugate is, and then see if you can apply what we've learned to do that one. Again, so yeah, we'll see how we do. I think you should be able to try that one. Okay, let's come to the last couple for the day. So the last things we might need to do for our limits is just do what we call simplifying a rational expression. And 9 times out of 10, what that means is use a common denominator to add and simplify. Usually that's what that means. Okay, so let's look at this one. And we need to what happens if you plug in h equals 0. So of course you get 1 over x plus 0 minus 1 over x over 0, and that is equal to 0 over 0, dead end, right? So we can't just sub it in. What can we do here? So limit as h approaches 0. Okay, let's look at the top and see if we can't do a common denominator. So I've got 1 over x plus h minus 1 over x. Now to make a common denominator, I need to make sure this fraction has an x and this fraction has an x plus h. Now don't lose track of what you're doing here. Remember, all of this is still over h, right? All I'm dealing with is just that first part. What am I trying to do here? I'm trying to make sure that these two denominators are the same so that the numerators can be added together. Okay? Let's look at what it looks like in step 2. So once again, the limit as h approaches 0. Now, on this side, I have x over x plus h times x. Then I have minus x plus h over x plus h times x. And all of this is still over h. So that's what I've got. Okay, so you see I basically just used now I notice that they have a common denominator. And let's go to the next step here. So we would just label this. This is 1, this is 2, this is 3. Okay, so the limit as h approaches 0. On the top so remember, when you are joining things together with a common denominator, you just join them together. Make sure that h is negative though, right? Because remember, you're subtracting that. You're subtracting this term x plus h, so that negative will have to distribute. And all of this is still over h. Okay. Limit h approaches 0. Okay, what do we have on the top? We have a negative h over x plus h times x, all of which is over h. Now remember, to divide by h equals to multiply by 1 over h. Right? When you divide by h, you multiply by 1 over h. Let's write it out in words. Divide by h equals multiply by 1 over h. So, I'm just going to write it slightly differently. Limit h approaches 0, negative h over x plus h times x times 1 over h, like so. Right? That just deals with the division part at the bottom. Okay? This brings me to my last step. Limit as h approaches 0. I have negative h over x plus h, x, and h. You can see now that it's possible for me to cancel those, and I get limit, move the page a little bit here. Limit as h approaches 0 of negative 1 over x plus h times x, and what can I do here is I get equals negative 1 over x squared. So I can, at this point, I guess I can still write limit as h approaches 0. I subbed in h equals 0, right? Sub in h equals 0. Remember, that's your ultimate goal when you're doing a limit, is to sub in the value that they've asked. Now, of course, in this question, it works a bit differently because they're asking you to sub in h, and they haven't left, like x is still a variable. So our final answer is not going to be a number like it was in other ones. Our final answer is going to be an equation that still has x in it. The whole issue here, remember, is we could not sub in h equals 0 at the beginning because it made the answer indeterminate. And in fact, all the way along, there was never an opportunity for us to sub in h equals 0. Until we canceled it right down here at this penultimate step, and then we could sub in h equals 0, right? You can sub in h equals 0 into this part where you get x plus 0 times x. You can sub into that, no problem, right? So your final answer is this. Let's do one last one, and then that'll be good for now. Okay, so here. Again, the bottom is not a common denominator. I want to make the bottom a common denominator. So limit as x approaches 3. The top, you know what? The top looks to me like we should factor it. So let's factor x minus 3 and x plus 3. Now for the bottom, I have a 1 over x, and then I have a 1 over 3. To make sure they have the same denominator, I'm going to multiply this one by 3 over 3, and this one by x over x, right? And that's going to make sure that both of the denominators are 3x. Okay, so now limit as x approaches 3. The top, x minus 3 multiplied by x plus 3. The bottom, 3 take away, let's do it this way. 3 over 3x take away x over 3x. Now again, those are the same denominator, so they can be joined together, right? That's the whole point of making a common denominator. They can be joined together. So limit x approaches 3, x minus 3, x plus 3 on the top. On the bottom, 3 take away x over 3x. Now, think back to what I just said before. To divide by 3 minus x over 3x, multiply by its reciprocal, right? So I'm asking you to divide. This fraction is your denominator of your big fraction, right? How do you divide by a fraction? Multiply by its reciprocal. So look at it again. X minus 3, x plus 3, multiplied by 3x over 3 minus x. Okay, that's what we're looking at. Okay, now why is this useful? Let's take all the stuff multiplying and put it in the numerator. X minus 3, x plus 3, 3x, and then all the stuff in the denominator. Now it kind of looks like we're stuck here, right? Because I look and it's like I don't really see anything that's the same for me to cancel. So I want you to remember this because this is really important. A minus b is the same thing as negative b minus a. You can always reverse whatever's inside a bracket by simply changing the sign out front. Why is that useful here? Because if you do that to the bottom, if you factor out a negative 1 from the bottom, now you realize, oh, actually there is something I can cancel here. I canceled this one. Oh, jeez, that was not so smart. How did that become an... Oh, I'm holding the pen upside down. That one and that one cancel, okay? And you're left with the limit as x approaches 3 of x plus 3, 3x, negative 1. Now, is this done? Yes. All I have to do is plug in the 3. As soon as I can plug in the 3, remember, my question's finished. So I get 6 times 9 divided by negative 1, which is, oh boy, negative 54. Okay, and that's my answer. Let's check that one because it looks like there's a lot of possibility for error. And then we'll call it a day. So f of x is x squared minus 9 on the top divided by 1 minus x minus 1 over 3 on the bottom. And that's what our equation looks like. We're looking for the limit as x approaches 3. So as x approaches 3, oops, okay, you can see the function does not exist. So there's a hole at that point, although of course you wouldn't notice it from a graph like this one. You'd have to investigate it. The function does not exist, but the limit does exist, and the limit is negative 54, just as we said. So for today, okay, a couple of things. There's some homework that you should try. I want you to do this one, like respond to this one on the discussion forum, or at least see if someone else has done it, if you agree with what they did. And it is very important to do the quiz, the test quiz there, so to make sure you're capable of uploading your work. Okay, so there's a link to that on the main page. Have a great day, and I will see you tomorrow.